what is the Chomsky hierarchy? What are language design principles? And how do these linguistic ideas tie to computer science?
Yeah. So let's start of let's start at as close to first principles as we can get, which is in our product, we decided that weak supervision was going to be one of the tools that we use to solve the labeling problem. What we realized is that weak supervision at its heart, these labeling functions, are really like search functions in a lot of ways. You're returning a true false value for a particular predicate. So given some input, you're assessing some logic and you're returning true or false. That same function signature exists in search engines. Like, do these pages have the pattern that you're looking for? Is it similar to what you're looking for? It's like a yes or no question, right? And you can rank it, obviously. You can say like how similar it is and that sort of thing. So fundamentally, if you think about it from like a first principle standpoint, this is a search problem. So the tools that people have been using historically to create labeling functions, and I say historically, it's really only been a thing for the last couple of years, are really like programming languages. It's Python and stuff like that, the lingua franca of the data science world. And that makes sense. However, it, number one, raises the barrier to entry for folks who want to be able to create labeling functions that may not know Python. And two, requires like a fair amount of understanding of the underlying data structure. So for instance, like you could imagine a labeling function that runs a regex on some text. Great. If your text is, or if your input is like a CSV or something, like you could imagine that you're running it over like a particular field or a set of fields or something. But if you want to like index into some data, if you want to like index into a PDF that's been OCR'd and there's like this data structure that you now have to like interact with, that's like a non-trivial thing for you to wire up when really the thing you're just trying to do is like run a regex, right? So that's sort of like point number one. And point number two is we saw an inherent need to automate the process of weak supervision. And what I mean by that is weak supervision at its core, you can think of it as like an ensembling technique. You're creating large quantities of independent sources of signal and you're combining them in ways that produce labels. So really like the weakly supervised process is just ensembling. And the question is, what sort of interesting signals can you introduce and like how independent are they? How many different varieties, like how much of the problem do they capture? So weakly supervised systems benefit from creating large quantities of these heuristics very quickly. And if you're sitting there just coming up with things off the top of your head, it's going to take you a long time. You know, even creating one labeling function will take you several minutes. But your problem might be correctly solved with like 200 labeling functions. You don't know ahead of time. Right. So are you going to spend all that time just coming up with stuff off the top of your head? Probably not. So we need ways to generate labeling functions. And the problem is Python and pretty much every programming language today can't easily be generated, at least not in a safe way. So this lends itself to like the halting problem, for instance, where given some program, you can't predict ahead of time if that program will terminate or not, unless like running it. So like every Turing complete language suffers from this particular problem. So if we were to generate just arbitrary Python, we don't know ahead of time if it's going to be safe to run, right? So that means that we have to constrain the space that we're generating somehow. And that lends itself to a different, what's called formal grammar, right? And this is where Noam, like Chomsky's hierarchy comes in, where you have different types of grammars. So the extremes are, what is it, like infinitely recursive? I forget what it's called. Let me actually quickly Google this. Unrestricted grammars. That's what it's called. That's basically like a Turing machine, right? It has like an unlimited amount of context that it can pull from. You have variables that are defined like somewhere else in the program that are eventually used downstream. Like it requires a lot of context to evaluate this thing. Versus at the very bottom layer of the hierarchy, you have what are called regular grammars. which, as an example, you have regular expressions. And these are just things that can be processed by like finite state machines. And the reason why this is important is if you think about a regex, if I have the regex ABC, all that means is in some text, I want to find ABC and return true if I find it. So what I can do is I can actually take the letters ABC and turn it into a finite state machine. I can just say, I start, if I find the letter A, transition to the next stage. If I find the letter B right after that, transition to the next state. If I find the letter C right after that, transition to the next state. I didn't need to know anything. I didn't need to retain any information about the previous values that were found or anything that's later on, really. I can evaluate this linearly and I can scan through the text from left to right, let's say, and I can process this thing in line, which means that I can efficiently process this and I can calculate if this thing is going to terminate or not. Interesting side note, most regex implementations in like Python, Java, that sort of thing are actually non-regular. They don't conform to the regular grammar anymore. And that's because people over time have added interesting features like arbitrary forward look-aheads and back references and that sort of thing. That's beside the point. So what we do is we had to constrain the grammar that people were able to use to query data so that we could then simulate it. We could generate it and we know it'll terminate. We know we can evaluate it efficiently. So that implied that we had to basically build a new language. Now, before you design a language, you have to choose, like you have to choose not to use all the other languages that exist, right? So we had to have very good reason to do that. And you know, when we talk about search queries, like there are lots of search technologies out there that have done exceptional jobs. Elasticsearch is one that immediately comes to mind. So the question that we often get is like, why not just use Elasticsearch? Like, why did you have to invent your own thing? And the thing that we realize is that counterintuitively, labeling is a small data problem. You have a finite fixed data set, typically, that you're interacting with. You're usually not labeling in an indefinite way. Right. You typically take a sample from a larger set that you believe is representative, you put it somewhere, and you have labelers interact with that. And that data set doesn't change for the duration of that period. So what that means is that Elasticsearch, on the other hand, was actually designed for very large data problems. It was designed for problems where the data actually does need to be split out across many machines and it can't be fit on a single machine. So they designed clever ways to interact with that sort of data. We don't have that problem, right? And in fact, we have the inverse problem. We have data that can fit on a single machine or parts of data that can be fit on individual machines, let's say. And we want to interact with that data as quickly as we possibly can. Again, to stay in that flow state. How do we do that? So things like Elasticsearch didn't quite work. And not to mention, like, the language itself became cumbersome for the types of things that you'd want to do from a labeling perspective. You don't just want to be able to do things like keyword searches. You want to be able to do things like similarity searches, like how close is this thing to this other thing? You want to be able to do things like database lookups, like all sorts of stuff. So we had to create our own language, which then implies that we had to create our own query engine, you know, the thing to process the language and turn it into something that we can evaluate, which then also implies that there is a data structure that we've created that allows you to efficiently index in the ways that you'd want. So whether you're doing full text classification, whether you're doing NER, like a segmentation type problem, even into images, video, audio, etc., we believe that all of these problems share the same relative footprint, where I have bytes that are laid out in some way that makes sense to the machine and to the users, but I have bytes fundamentally, and I have a graph that points into those bytes. So the graph, nodes in the graph could be things like hand labels that people have created, and said, okay, this part of the text is such and such label. It could be these labeling functions that are pointing into the data and be like, these are the parts of the data that I affect. You know, it could be what we call derived labels, things like labels that are predicted. So probabilistic labels that we generate from, you know, the combination of all your different heuristics. Fundamentally, these are all just like nodes in a graph that are pointing into data. And to access that data, you could either access the data directly, or you could go through the nodes and say, show me everything that has a greater than 90% likelihood of being such and such class. Or show me everything that this person is hand labeled over this period of time. Like all of that is just metadata stored in a graph that indexes into this data. So we have this like stack of things we had to build in order to do the really cool thing, which we're really excited about, which is that suggestion engine. And that suggestion engine, because we've optimized the entire stack, because we can do things like sub-millisecond latency, like on queries, that means that we can run over 1,000 queries every second. A user is not going to sit there and do that. A user is not going to type out a query, in a sub-millisecond time, but the machine can. So while the user is doing stuff, while the user is labeling, interacting with the product or whatever, we have a simulation engine that's running in the background, constantly trying all the possible queries that a user might want to do, and then weighing out the probabilities and choosing the things that are very likely predictive of the class and showing them to the user. Or in the case of Copilot, checking them in and maintaining a set. And the really cool bit about that is you don't necessarily, in the world of Copilot, you don't necessarily even need a human to be sitting there driving it. If you happen to have already labeled data that you might have labeled at some point in the past by hand, you can run it through this process, and Watchful will act like a human is sitting there saying yes, no, yes, no, yes, no. But in fact, it's just your data, and the simulation engine is creating all the heuristics that it would take to basically explain those labels. So you could give it already labeled data, and you get out like heuristics that you could use to label all your data, not just that sample, in exactly the same way. But now it's all explainable. You can go back and be like, all right, this function is not quite right. Here's how I want to tweak it and that sort of thing. So yeah, we have to go really deep on this. But we ended up with like a very interesting solution.